Researchers have created a device that enables them to electronically steer and focus a beam of terahertz electromagnetic energy with extreme precision. This opens the door to high-resolution real-time imaging devices that are hundreds the size of other radar systems and more robust than other optical systems. Terahertz waves, located on the electromagnetic spectrum between microwaves and infrared light, exist in a no man's land, where neither classic electronics nor optical devices can effectively manipulate their energy. But these high-frequency radio waves have many unique properties, like the ability to pass through certain solid materials without the health effects of X-rays. They may also enable higher speed communications or vision systems that can see through foggy or dusty environments. The Terahertz Integrated Electronics Group at MIT seeks to bridge this so-called terahertz gap. These researchers have now demonstrated the most precise electronically steerable terahertz antenna array, which contains the largest number of antennas. The antenna array, called a reflector array, operates like a controllable mirror with its direction of reflection guided by a computer. The reflector array, which packs nearly 10,000 antennas onto a device the size of a credit card, can precisely focus a beam of terahertz energy on a tiny area and control it rapidly with no moving parts. Built using semiconductor chips and innovative fabrication techniques, the reflector array is also scalable. The researchers demonstrated the device by generating 3D depth images of scenes. The images are similar to those generated by a LiDAR, light detection and ranging device, but because the reflector array uses terahertz waves instead of light, it can operate effectively in rain, fog, or snow. This small reflector array was also able to generate radar images with twice the angular resolution of those produced by a radar on Cape Cod, which is a building so large it is visible from space. While the Cape Cod radar is able to cover a much larger area, the new reflector array is the first to bring military-grade resolution to a device for commercial intelligent machines. With typical antenna arrays, each antenna generates its own radio wave power internally, which not only wastes a lot of energy but also creates complexity and signal distribution challenges, which previously prevented such arrays from scaling to the number of antennas required. Instead, the researchers built a reflector array that uses one main source of energy to fire terahertz waves at the antennas, which then reflect the energy in a direction that the researchers control, similar to a rooftop satellite dish. After receiving the energy, each antenna performs a time delay before reflecting it, which focuses the beam in a specific direction. The phase shifters that control that time delay typically consume a lot of the radio waves energy, sometimes as much as 90% of it. They designed a new phase shifter that is made from only 2 transistors, so it consumes about half as much power. In addition, typical phase shifters require an external power source such as power supply or battery for their operation, which creates problems with power consumption and heating. The new phase shifter design consumes no power at all. Steering the beam of energy is another problem. Computing and communicating enough bits to control 10,000 antennas at once would dramatically slow the reflector array's performance. The researchers avoided this problem by integrating the antenna array directly onto computer chips. Because the phase shifters are so small, just 2 transistors, they were able to reserve about 99% of the space on the chip. They use this extra space for memory, so each antenna can store a library of different phases. To achieve their desired performance, the researchers needed about 10,000 antennas, but building a computer chip big enough to hold all those antennas is a huge challenge in itself. So they took a scalable approach, building a single small chip with 49 antennas that is designed to talk to copies of itself. Then they tiled the chips into a 14 by 14 array and stitched them together with microscopic gold wires that can communicate signals and power the array of chips. The team worked with Intel to fabricate the chips and assist with the assembly of the array. They demonstrated the reflector array by taking measurements called the radiation patterns, which describe the angular direction in which an antenna is radiating its energy. They were able to focus the energy very precisely, so the beam was only 1 degree wide and were able to steer that beam in steps of 1 degree. When used as an imager, the 1 degree wide beam moves in a zigzag pattern over each point in a scene and creates a 3D depth image. Unlike other terahertz arrays which can take hours or even days to create an image, this works in real time. Because this reflector array works quickly and is compact, it could be useful as an imager for a self-driving car, especially since terahertz waves can see through bad weather. The device could also be well suited for autonomous drones because it is lightweight and has no moving parts. In addition, the technology could be applied in security settings, enabling a non-intrusive body scanner that could work in seconds instead of minutes.